Hi everyone, welcome to ML++ with Omkar. In this video, we are going to go over a problem which is important in terms of pure linear algebra as well as really critical in the world of machine learning as well. The problem is calculate eigenvalues of a matrix. Now, before I go ahead with the solution, discuss the approach and all of that, the full credit for this problem being hosted on this website goes to deepml.com. This is a website which has a wonderful collection of problems related to machine learning. Do check it out. Without any further ado, let's get into the problem. So the problem is quite simple. Write a Python function that calculates the eigenvalues of a 2 by 2 matrix. The function should return a list containing the eigenvalues sorted from highest to lowest. So they have given some logic here as well. I mean, this is basically the characteristic equation that has been given to us for a 2 by 2 matrix. So people who are really familiar with how we derive the characteristic equation for any matrix in order to get to the eigenvalues and eigenvectors may skip this particular part of this video and directly jump into the code implementation. I will, however, go through some of the fundamentals of the intuition behind why the characteristic equation comes out to be what it is. Let's jump to the OneNote board. Right, let's get started. This is some blue color. Perfect. Now, to begin with, what exactly are eigenvalues? Let's say we have some matrix called A, right? What eigenvalues say is that, you know what? So let's understand in terms of eigenvectors. So eigenvectors is some vector V such that if you apply this particular linear transform on that particular vector, it will still remain in its span. It will just be stretched or collapsed or remain as it is on its span. So what that means is this will result in lambda times V, where lambda is your required eigenvalue. Now, what this effectively means is that let's say you have some matrix here. Let me just fill in some values for the sake of simplicity. Let's take some vector 1, 2, right? So if I try to, let me use some other color to plot this out on a 2D plane. So if I try to plot this vector, right, 1 and 2 on a 2D plane, let's just think in terms of physics for a moment. I mean, this is mathematics as well, but all right. So this is 1, this is 2, this is how our original vector would look like, right? So this is V. Now, once this transformation is being applied, what will that result in is this is 2 into 1 plus 0 times 2, then 1 into 3 plus 3 into 2. This results in 2 and this is 3 plus 6, which is 9. So this is 2 and 9. So if I try to plot this now, 2 and 9 would be somewhere very high along the axis, somewhere along here. Clearly, these two are not the same vectors. So basically, for a vector, we can define the span as extend that vector in both this, in all of its directions. Basically, this is a two-dimensional vector. So we just have this couple of directions, but basically you extend the vector in whichever plane or whichever system it lies in. It can be 3D, 4D, or whatever. You just keep on expanding it, passing through origin. That is the span of the given vector. And what if the given vector is a eigenvector for a given matrix? If you apply the particular matrix as a transform to it, it should not be thrown off its span. In this case, it is getting thrown off. So clearly 1, 2 is not the eigenvector for the given matrix. So in short, that is the idea behind the eigenvector. And this eigenvalue is basically a measure of how much stretching or how much compression that will happen. So basically, if V was eigenvalue, let's say after applying the transformation, this the resulting vector is something like this. So this extended value, right? So this is the times of expansion that the original vector v went through, which is your lambda, which is your eigenvalues. Now this is very, very important because this helps us in a number of things. For example, we use this to do image compressions. We use this to find the most important variables for machine learning models, like those features which have the highest variance, because for any given matrix, if you are able to find its eigenvectors corresponding to the highest eigenvalues will store the highest information, because they are sort of like, you can think of it as the characteristic vectors of the given matrix, right? So you can think of it as principal vectors of a given matrix, right? So they define the matrix, right? So enough about eigenvectors. Now going to how we compute these things. The characteristic equation comes now, so that will come from this particular equation. So if we take everything to single side, what you can get is, so if we take a lambda minus lambda v gives us 0. So this is v vector, my bad. So if we take v vector as common, uh, it is a minus lambda I, giving you 0, right? Now, if we think about it, if we have a system of equations which is bx equals to 0, b is, let's say, some matrix, x is some vector, right? In this case, this is our matrix. Actually, I have roofed up the ordering. Ordering should be something like this. This is not the ordering. Again, to be clear, this is just for the purpose of dimensionality matching. So something n cross 1, n cross n, this is not a correct match. The match is between n cross n and n cross 1, leading to n cross 1 vector eventually, right? So if we have some given equation like this, where b is a matrix, x is some vector, and if we want non-zero solutions for x, then the only way it is possible is rows in B must be dependent on each other. That's the only way you will get non-zero solutions. And once rows of a matrix become dependent on each other, the matrix has determinant 0, or it is non-invertible or singular. In other words, determinant of B has to be 0. Why? Because the rows of this matrix have to be dependent if we are claiming that it has non-zero solutions. Now, using this idea in this original equation, if we want non-zero solutions for this to get our eigenvectors, then A minus lambda I must be a singular matrix, which means determinant of A minus lambda times of I must be 0. This is the origin of the characteristic equation. The reason being that if you have a 2 by 2 matrix, so let's say you have A, B, C, and D, this is your A, and so what this effectively would look like is A minus lambda, B, C, D minus lambda, right? This determinant should be equal to 0. If you try to find the determinant, it's basically A minus lambda times D minus lambda minus BC equals to 0. Remember, this is how we can compute the determinant, right? Multiply this, subtract this. So expand this. This is AD minus A lambda minus lambda D plus lambda square minus BC equals to 0. In other words, lambda square minus lambda A plus D plus AD minus BC equals to 0. This is the characteristic equation that comes out. If we simplify this in terms of matrix algebra, this is lambda square minus lambda. A plus D is the trace of the original matrix. A plus D, this is the trace of the original matrix, and AD minus BC is effectively the determinant of the original matrix, if you think about it. So this is trace of A plus determinant of A. This gives us 0. This is the characteristic equation for a 2 by 2 matrix. So same thing we can do for a 3 by 3 matrix as well. We have like all these things you will have. This is just 3 by 3, and then you do the computation that we do. In that case, however, computing determinant is difficult. Like we do plus, minus, plus, and all those linear algebra rules will come into picture. But that's beyond the scope of this particular video. So for this particular video, this is the theory that we are going to go ahead. Now, Going back to the question, they have already mentioned this, which is trace of a determinant A. We just need to return the eigenvalues. And just a quick note here, they want the eigenvalues sorted from highest to lowest. That is usually how we should return the eigenvalues when you are writing any library. I mean, we already have libraries in NumPy, which will return you the eigenvalues in sorted order, descending order. The reason being that eigenvector corresponding to the highest power of an eigenvalue gives you the highest variance or highest information. So usually for image compression, we'll just pick some eigenvectors which correspond to the highest eigenvalue that will have the maximum information. That will define the matrix. It will use least amount of information possible, but have the most. It will use the least amount of data possible, but have the most amount of information. Anyways, coming back to this question, we have been given a list of so this is a list. Inside this, again a list. We have float, and I'm not able to understand this formation. What is this list of list? Oh, float or integers, correct. So, all right, how do we do this? So what I need to define is, okay, so here we just need to find the roots. I mean, of course, if you want to find solve for lambda, you just need to find the roots. So let's just define trace. Should I define A, B, C, D first, right? Yeah. So let me do something like this. Will it be worth it? Let's just directly define. I mean, that will be even more painful. So this is I0, B is matrix of I1, C is matrix of 0, 0, 0, 0, 0, 1. A, B, C is this. This is 0. And D is this. Now, we want to define the trace. Trace is simply A plus D. Det is A times D minus B times C. Now, once we have the trace and the determinant, we know how to find the roots of any quadratic equation. If you have equation ax square plus bx plus equals to 0, roots are minus b plus or minus discriminant by 2 times a. So here, if you look at our original equation or in any 2 by 2 equation, a is basically 1. So we just have a denominator of 2, and b is negative of trace, right? So let me just define this. B is minus 1 into trace, right? If you just compare, A is 1 and C is determinant as it is, right? So your discriminant is, I think square root function is available in Python directly. Square root of B square minus 4AC, this divided by 2 divided by 2 times A. This is your discriminant. Discriminant is just this part, my bad. So you have the discriminant b square minus 4 is equal to square root. We have minus b plus or minus discriminant by 2a. So lambda 1 is minus 1 into b plus d divided by 2a. And similarly lambda 2 is minus b minus of d divided by 2a. So these are the things. And if I want to return a list, so eigen values, I just define it here. So I need to return in descending order. So lambda 1 and lambda 2. So this should be fine. So please note that, I mean, of course, code could be more efficient, but just for simplicity's sake, I have written it in the simplest way possible. Right? Just define the elements, write down the trace, the determinants, then define the coefficients for x square plus bx plus c. You compute the discriminant. Discriminant is b square minus 4ac, right? And yeah, I think there is one mistake. So this is, yeah, this is negative of trace, correct. So this is negative of trace. You have the trace. Negative of trace is a b, and all the things are defined. We computed d and minus b plus minus this. This will always be positive. Should work. Let's see. So both failed for the reason square root is not defined. So what do we use? Import maths. Do you have to import math or something? Is this going to work? Can I just import something? Import maths. Maybe. Again, this is just a syntax thing. I wouldn't really be worried about. Okay, so this problem is solved, right? If we go back to the problems list, this should appear solved. Yeah, cool. So this was all about this particular video, calculation of eigenvalues for a given matrix, both theoretical understanding regarding it and the implementation in code. Now, of course, this is just a 2 by 2 matrix, which is fairly simple. If it becomes a general n by n matrix, things will be more complicated, but that's for a different video, not in this video. I hope you understood something, at least theoretical speaking, and from a code point of view, and things are a bit more clear for you right now. That's all I can hope for. Thanks for watching. Like, share, and subscribe if you find this video interesting. Thank you.